Welcome to The Explainer. Today, we're diving into one of the most important ideas in all of chemistry, the mole. It's the secret key that lets chemists count things that are basically, well, uncountable. So here's the game plan. We'll start with why we even have this problem in the first place. Then, we'll meet the chemist's clever solution, the mole. We'll see how that lets us use a simple scale to count atoms, apply that to chemical recipes, and finally, get a reality check on how it all plays out in the real world. You've definitely seen this before, right? You look at a food label and you see ingredients listed in grams. But here's the thing. An atom is so unbelievably tiny that grams are a ridiculously huge unit to measure a single one. It just doesn't work.
And that gets us to the core problem for any chemist. You want to make something, you need to know how many atoms you're starting with, but how do you do that? It's not like you can see them or pick them up and count them one by one. It seems impossible.
So how did they solve this? Did they invent some kind of super microscope? Nope. They used something much more powerful. A really, really clever idea. Let's get into it. To get your head around this, just look at the pictures for a second. We use words to group things all the time just to make life easier. You know, a pair of gloves is always 2. A dozen donuts is always 12. They're just convenient words for a specific number.
Well, chemists needed their own counting word. But because they were counting atoms, it had to stand for a truly, mind-bogglingly huge number. And the word they came up with was the mole.
And here is the absolute key. A mole is just a specific amount of stuff. That's it. It's the chemist's dozen. So a mole of iron atoms has the exact same number of particles as a mole of water molecules. It's our standard quantity. So how big is the chemist's dozen? It's this number, a number so famous it gets its own name, the Avogadro constant. It's 602,000 billion. I mean, if you had a mole of basketballs, you could create a new planet the same size as Earth. It's a crazy big number, but it's the perfect size for counting atoms. Okay, knowing this number is one thing, but what makes it so incredibly useful? This is the part that's pure genius. This is how we connect this huge abstract number to something we can actually do in a lab, like just weighing something out. Okay, here's the trick. You see the relative atomic mass on the periodic table. It's just a ratio, no units. Now, look at the molar mass. Here's the magic. The mole was defined on purpose so that an element's relative atomic mass number is numerically the exact same as the mass of 1 mole of it in grams. This wasn't a coincidence. It was brilliant design. And this works for everything. Iron's relative mass is 56. 1 mole of it weighs 56 grams. Water's is 18. 1 mole is 18 grams. So if you go into the lab and weigh out 56 grams of iron filings, without counting a single atom, that you have exactly 1 mole. You are counting by weighing.
Now, to make life even easier, chemists love using these formula triangles. They're basically a visual shortcut for the math. You just cover up the thing you're trying to find, and the triangle tells you what to do. If you want to find the number of moles, cover it up, and you see it's just mass divided by molar mass. It's a fantastic little tool.
So now that we can count atoms just by weighing them, we can actually start to build things. And that brings us to our next big idea, stoichiometry. Yeah, I know, it's a huge word, but I promise you all it means is a chemical recipe. Seriously, think about making a smoothie. The recipe doesn't just list ingredients, it gives you a ratio. For every 1 orange, you need 2 bananas and 5 grapes. You can't just chuck stuff in and hope for the best. The ratio is what matters. A balanced chemical equation is exactly the same thing, just for molecules. Those big numbers in front of the formulas aren't telling you the mass, they're telling you the recipe's ratio in moles. Take a look at this equation. There's no number in front of the magnesium carbonate, which means there's a 1. There's a 2 in front of the hydrochloric acid. So this chemical recipe is telling us, for every 1 mole of this first ingredient, you need exactly 2 moles of the second one. It's a 1-to-2 mole ratio. Simple as that. And because we know that, we can perfectly plan our reactions. You just follow these 3 steps. First, figure out how many moles of the final product you want. Second, use the recipe's mole ratio to find out how many moles of your ingredients you need. And third, turn those moles back into grams so you can weigh them out. Okay, but just like when you're cooking, things in a real lab don't always follow the recipe perfectly. So we need to talk about what happens when chemistry gets real.
Let's go back to our smoothie. The recipe says you need 2 bananas, but you only have 1. Well, you can have a mountain of oranges and grapes, but as soon as that single banana is gone, you're done. You can't make any more smoothie. In chemistry, we call that the limiting reactant. It's the ingredient that runs out first and stops everything.
And because of things like that, or maybe the reaction just isn't perfect, the amount of stuff you actually make, your actual yield, is usually a little less than what the recipe promised, which we call the theoretical yield. We measure how successful we were with something called percentage yield. Now, why does any of this really matter? This quote says it all. Purity is the other side of the coin. When you're talking about food, or especially medicine, having unwanted extras isn't just wasteful. It can be flat out dangerous. So getting the highest purity possible is critical. And you see this idea everywhere. Sometimes, like with gold, you actually make it less pure on purpose. Pure gold is too soft for jewelry, so you mix it with other metals to make it stronger. But with medicine, it's the complete opposite. You want it as close to 100% pure as you can possibly get for it to be safe and effective. So let's wrap this up. What are the big takeaways? The mole is our special counting number for the atomic world. Molar mass is the brilliant trick that lets us count those atoms just by weighing them. Stoichiometry is just using a balanced equation as a mole recipe. And finally, concepts like yield and purity are our reality checks. At the very center of it all is the mole. It's the fundamental bridge from the invisible world of atoms to the world we can see and measure. It's amazing, really. This one single idea lets us build and understand our world on a molecular level. And it leaves you with a bigger question to think about. Where else does a single, powerful idea like this help us make sense of our incredibly complex universe?